In this example, we will find all solutions for 3 times cosine of 2x plus cosine of x plus 2 is equal to 0. We're going to keep all answers exact. Note that this question says to find all solutions, which means that we are going to find infinite solution sets that would satisfy this for all values of x. Now in this case, I have 3 times cosine of 2x plus cosine of x. Some may look at that and say, hey, you have 2 of the same trigonometric term. They are both cosine, but they're not the same trigonometric term because they have different inputs. One has 2x in it, the other one has x in it. So those are actually not the same trigonometric function realistically. They're going to act differently. So that doesn't work. We're okay with powers, but when you change the input, that makes it different. So I can't just use substitution here, at least not yet. But if I do want to try to manipulate this to maybe just get cosine of x's instead of 2x's, I do see that first term of cosine of 2x, and some bells should be ringing. Because cosine of 2x would connect to a double angle identity. And I say a double angle identity because there's a few of them available here. Cosine of 2x, we've established cosine of 2x could equal cosine squared of x minus sine squared of x. We also have 2 cosine squared of x minus 1, and we also have 1 minus 2 sine squared of x. These latter two being generated using the Pythagorean identity on the first one listed. But these are all typically listed as double angle identities for cosine of 2x, and the question becomes, which one do I want to use? Keep in mind that my goal here is to try to get to the same trigonometric function. If I were to try to use this first one, well, great, I now have cosine of x again, but I have now also introduced sine squared of x, so I don't want that. For the same reason, I'm not going to use the third one, 1 minus 2 sine squared of x. That involves sine of x, and my original equation is all about cosine. I could use that third one, but then that would require a little bit more manipulation that I'd have to maneuver through. So instead of those, I'm going to use the middle identity here, 2 cosine squared of x minus 1. I'm going to use this identity and replace that where I see cosine of 2x. I chose this one because the only trigonometric term that this one involves is cosine of x, which is already a trigonometric term in my original equation. So, what that's going to look like, 3 cosine of 2x plus cosine of x plus 2 equals 0. I'll replace this term here with 2 cosine squared of x minus 1. Careful that means that this 3 is going to be distributed to both terms there, to both the 2 cosine squared of x as well as the minus 1. That will now give me then 6 cosine squared of x minus 3 plus cosine of x plus 2. Or 6 cosine squared of x plus cosine of x, and I'll combine the two constant terms, minus 3 and plus 2, to make minus 1. Alright, so all I've done right now is replace cosine of 2x with a double angle identity and distribute it accordingly. But now I have an expression, an equation here, that involves cosine of x taken to a second power, but remember that that's really just the same as cosine of x squared, so it's still cosine of x, as well as another cosine of x. So I have an equation involving the same trigonometric function. If you would like then at this point to use substitution, if that makes it look a little bit easier for you, by all means. I will call in this case for the time being, let's say cosine of x, I'll call that a. So then I'll have 6a squared plus a minus 1 is equal to 0. Now that 6a squared plus a minus 1, that is a polynomial. And I should be able to factor that out. I should be able to fix that up in order to get two terms that multiply to equal 0. There are a few methods that you can use to approach this. If it is difficult to come up with two multiplied terms that equal 0, you can always go to the quadratic formula. That still works with these kinds of quadratic functions. In this case, though, if I want two terms that multiply to equal 0, two binomial terms, well, minus 1 is pretty easy. That means I'm going to be using plus 1 and minus 1 in some way. So plus 1 and minus 1. At least if this comes out as nice values. And then for 6a, that can be made by doing, say, 6 times 1 or 3 times 2, or possibly negative versions of those. Negative 6 times negative 1, negative 3 times negative 2. But if it's combining to make a in the middle, it's probably 3 and 2 so that they are pretty close to each other, and the difference is just a value of 1. In this case, I should have 2a and 3a in that particular order. That way, my two constant terms create negative 1. My two terms involving a make 6a squared. And my two terms I would add in the middle, I'd have minus 2a as well as plus 3a. And that'll give me plus a in the middle. Again, there are a few different ways of approaching this kind of problem to do that. I just went through that using problem solving, using logic per se. At this point then, I have two terms multiply that equal 0, so I can set 2a plus 1 itself to equal 0, as well as 3a minus 1 equal to 0. Or if I solve for a there, and then replace a with cosine of x, subtract 1 and divide by 2, that will give me negative 1/2. That will equal a, otherwise known as cosine of x. And for the second equation, add 1, divide by 3. That will give me 1/3 positive, also equals cosine of x. So there I implemented substitution to clean up the equation a little bit more, and then substituted it back to get back to the original question involving x. Now again, you didn't need to do substitution, but it does help to make it look a little bit easier. But at this point, we now should be able to come up with all solutions of x. Keep in mind that we are looking for all solutions, not within a particular interval. Our final answer should be infinite sets of solutions. Starting with cosine of x equals negative 1/2. That happens to be a ratio I know from the unit circles, so I should be able to evaluate this a little bit more simply. Cosine of x I know equals 1/2 at multiples of pi over 3, but it's a negative 1/2, so that would be the quadrants where cosine is negative, which would be quadrant 2 and 3 of the unit circle. So that means in quadrant 2, where cosine equals negative 1/2, that would be at 2 pi over 3. And then any coterminal solution would be available as well. And then also in quadrant 3, where cosine equals negative 1/2, that would be at 4 pi over 3. That would also be plus 2 pi k. In all these cases, k is an integer. Next, we can talk about cosine of x equals 1/3. Now I know 1/2 from the unit circle. I don't know 1/3 though. So there's not as much I can do about that. I know that it will be a little bit larger than pi over 3. I know it should be closer to the y-axis, but I don't know that particular angle measure from the unit circle. So when I use an inverse function to get cosine by itself, I will just keep it as that inverse function. So arc cosine of 1/3. And then that is plus 2 pi k. That would be one set of solutions. And then the other infinite set of solutions that is made when using arc cosine would be 2 pi minus arc cosine of 1/3 plus 2 pi k, or some write that as just negative arc cosine of 1/3 plus 2 pi k. That's also correct. But this would be our set of infinite solutions.